To the people of Europe, I bid good afternoon. To the people of the Americas, I bid good morning. To those joining us from Asia, I wish you a pleasant evening. And finally, to the chair for today's session, would you please do us the honor of introducing the first speaker?
Thank you, Niels. That was nice to be introduced by you. So welcome, everyone. I wanted to start by saying, good morning to those of us who are on the west side of the Atlantic and so on, but Niels preceded me. He said roughly that. So without further ado, our first speaker, whom I welcome, is Stefan Weinzierl. And he will tell us about elliptic Feynman integrals and modular transformation. So Stefan, if you could share the screen.
Yes. So you should see my screen now. Is that so?
I do.
Okay.
We do. Yeah.
So welcome, everybody. I will talk today about elliptic Feynman integrals and modular transformations. And let me start with some motivation. So I would start with an analogy. So we are here at the Amplitudes conference and just think about basically a scattering amplitude in a gauge theory. Then you could, in principle, express it as a sum of Feynman diagrams. And in principle, I'm not saying that you should do that, and most people at this conference don't want to do that, but in principle, you could calculate each Feynman diagram separately, and in doing so, you have to make a choice for a gauge. So the individual Feynman diagram, what you get out as a number, will depend on your gauge choice. And in the final end, the scattering amplitude, if you sum up everything, is independent of the gauge choice. So it does not really matter what gauge you choose. So that is a general principle stated very simply. But then if you look at the details, this can be really a little bit non-trivial. For instance, you can do the calculation of the Altarelli-Parisi splitting function in Feynman gauge and in axial gauge and try to see basically how terms are arranged there. And you will see soon get down to the gory details and find it a little bit technical. So I will not be talking about basically these things, but I will be talking about something else. That is Feynman integrals, which are somehow associated to an elliptic curve. So let's consider a scalar Feynman integral, which is associated to an elliptic curve. It's a scalar integral, so it's well-defined, independent of any gauge. So it's a well-defined quantity, so we can calculate that. Now we have an elliptic curve, and we basically can define an elliptic curve by a lattice. And for the lattice, we have to specify two basis vectors. We call these basis vector periods. So we make a choice for this basis. We compute the Feynman integral. We express everything in master integrals. In the end, basically, it's a linear combination of master integrals. We make this choice of the periods, and in the end, we get the result. You would say, of course, we should get the same result if basically in the beginning I made a different choice, a different legitimate choice for the periods as the one I originally chose. And that's basically what the talk is about. So suppose that I do the calculation, I choose two periods, psi2, psi1, and my colleague next door, he made a different choice. He chooses psi2 prime, psi1 prime. So our choices will always be related by a linear transformation by a 2x2 matrix gamma. And this transformation is called a modular transformation. So that's the second part of the title. What is a modular transformation? It's basically just the transition matrix going from one choice of periods to another choice of periods. So the question is, how do elliptic Feynman integrals behave under modular transformations? Now, let me fast forward basically and already state you some result on the simplest elliptic Feynman integrals. There you find, first of all, they can be written as iterated integrals of modular forms. I will explain what modular forms are in a second. But these modular forms are not modular forms for the full modular group, but just for some subgroup. Let's call this subgroup gamma. So that brings me exactly to two questions. Now, modular forms by definition have a nice transformation behavior under modular transformations for this subgroup gamma. But since this is only a subgroup, of course we ask, what happens if we do a modular transformation which is not in this subgroup? As a physicist, we see no reasons why we should restrict ourselves to this particular subgroup. That's the first question. The second one, which is even worse, is let's now restrict ourselves to this specific modular transformation from this subgroup. And we know we can express everything as iterated integrals of modular forms from this subgroup. Now do a modular transformation and see how these iterated integrals transform. And you find they don't transform into iterated integrals of modular forms, but to something more general. So we leave this function space. So that is a little bit weird. So the question is, what is going on here? And basically, how do we manage to stay inside this function space? And actually, both questions have a very nice answer, and they will be answered in this talk, and that's what this talk is about. So that was the motivation. Now we need a little bit background from physics, basically about Feynman integrals. So I consider scalar Feynman integrals, but allow the propagators to be raised to some integer power. And that is basically this nu here, which you see in the exponent. And I use the standard convention basically to write down this nu basically here as indices. So this Feynman integral will depend on some kinematic variables, which are either scalar products of the external momenta or the internal masses squared divided by some common scale mu, which introduce that everything is dimensionless. Now this mu is actually arbitrary, and I can use this freedom to set it basically that one of these variables basically is equal to 1, and then I only have to consider the other ones. So if I say I have nb plus 1 variables of this type, and I set one variable to 1, afterwards I have basically nb variables, which I have to really take into account. And basically I can consider all the integrals with any combination of these indices here, but integration by parts allows me to express any of those integrals as a linear combination of master integrals. So let's set up the thing. We have a number of master integrals, which in this talk I denote by NF, and just label the master integrals I1 to I2 up to INF. And I have a number of kinematic variables these master integrals depend on, x1 to xnb. So now you will probably ask, why did I choose these letters NF and NB? What do they stand for? Well, the whole situation is I can think about a vector bundle, basically a base space parameterized by my kinematic variables of dimension NB. And at each point, basically, of this base space, I have a vector space glued to it of dimension NF, and my master integrals are just sections in this fiber bundle. So that's basically where the notation comes from. Now, this vector bundle is equipped with a connection, and the connection is nothing else the differential equation we use basically to solve Feynman integrals. So again, by integration by parts, differentiating under the integral sign, I can derive always a differential equation for my master integrals. So basically that's the first step, that I get a differential equation for my Feynman integral can be done completely algorithmically. So I get basically a matrix here of dimension NF times NF, which may depend on the dimensional regularization parameter epsilon. and my kinematic variables as rational. The next step is that I try to put it into a simple form that the dimensional regularization parameter just occurs as a prefactor. Once I achieve that, basically I can systematically solve this differential equation order by order in epsilon, always using my solution from the previous order, plug it in and obtain by once integrating the solution as the next order. So the essential step is the step 2. Basically, I have to transform the differential equation into this form. Now, how can I do that? So there are two things which I can do. I can redefine my master integrals, saying that my old master integrals, if I multiply them by an invertible matrix, define my new master integrals. And if I do that, I change this matrix A from A to A primed. So this is basically a change of the basis in the fiber. So it's a fiber transformation. And it's basically, if you look at the formulas, it's very similar to what we do if you look at a Young-Mills theory and consider a gauge transformation. So this transformation formula is exactly the same as we would have for a gauge transformation. It's basically X dependent and basically tells you how basically the thing in the fiber transforms. In addition, we can change the variables on the base manifold. We can go from old variables to new variables. And also then, basically, if we write out this matrix A explicitly in the coordinates, they change according to a Jacobian factor if we go to new coordinates. So this transformation is very similar to what we do in general relativity, where we also say we can choose any coordinate system we like. So also here we say we can change the coordinates as we like. And usually we do that in the simplest cases to absorb square roots, which we might have in the variables x, but then are rationalized in the variables x prime. So these are basically the two things which we can use to transform our differential equation. Now let's go a little bit to the background from mathematics. We will be looking at elliptic curves. And for this talk, it's sufficient to think about the elliptic curve as a complex numbers mod a lattice. So points which only differ by a lattice vector we consider equivalent. So we have to specify a lattice, and to specify a lattice, which I've drawn here, basically it suffices just to give basically two lattice vectors, which I call basically psi1 and psi2. So these lattice vectors are also the periods of an elliptic curve. So I will always be using the word periods for these two things. So, but you see, basically, in order to define the lattice, I say, well, I give you basically two lattice vectors, psi1 and psi2. So mathematicians call the data where they say we have one elliptic curve, C mod lambda, plus a specified pair of lattice vectors which generates this lattice, a framed elliptic curve. So it's an elliptic curve with a frame. And of course, our general intuition is that the frame should not matter. So standard conventions is that we normalize our lattice, that one generator equals 1. The other one is then the ratio of the two. So basically we normalize psi1 to 1, and then the other one becomes tau, which is the ratio of psi2 divided by psi1. You can require that the imaginary part of tau is always bigger than 0, otherwise simply exchange psi1 and psi2. And that basically, if you require that, it means basically tau takes value in the complex upper half plane. Now let's come back to the situations that somebody else might change a different pair of periods. For instance, again, take this lattice, now generated by 1 and tau. That would be my choice. But now somebody else comes along and says, I generated by 1 and tau primed. It's exactly the same lattice. So, and basically I can calculate basically the new periods in terms of the old periods by a linear transformation, A, B, C, D. And since these are lattice vectors, the A, B, C, D are better basically integer numbers. Otherwise we don't get a lattice vector. Furthermore, the whole thing should be invertible. So that also means basically it must have an inverse, and the determinant must be equal to 1. So this matrix must be in that group here. And that group is called the modular group. Now, this transformation, basically, if you translate it, basically how the variable tau transforms into tau prime, it's just this formula here. So now we can look at specific nice functions which transform nicely under modular transformations. And these are modular forms. They have a transformation behavior under modular transformation. So this is the transform tau prime here. And it's given by the old one times basically an automorphic factor to some power k. And this power k is called the modular weight of this specific modular form. In addition, you require basically that f is holomorphic on the complex upper half plane, and it's also holomorphic at I infinity. It's also helpful to define a /k gamma operator by this formula here. And if you introduce this operator, then basically the first condition, which is basically rather explicit here, can be simply stated that basically f is invariant under this /k gamma operation. So now we look at subgroups of the full modular group. And the standard examples are the ones where you say one of the entries or several of these entries is 0 mod n. So let's think about n being 6, then the C is allowed to be 0, 6, 12, and so on, minus 6 as well. Or here, basically, you require basically that A and D in addition basically are equal to 1 mod 6. So basically 1, 7, and so on. So this defines what mathematicians call gamma 0 of n. This defines what mathematicians call gamma 1 of n. And this defines what mathematicians call gamma of n. So the last one is called the principal congruence subgroup of level n. So then basically to define modular forms for these congruence subgroups, you relax the transformation properties. You only require that they transform nicely under elements of this group, but not of the full modular group. Plus, in addition, you require holomorphicity on the complex upper half plane and at the cusps. That is as before. So now, the space of all modular forms for a given congruent subgroup gamma is denoted by mk of gamma. Now, the space becomes bigger as the subgroups become smaller. So basically it means that the principal congruent subgroup, the space of modular forms for those, is the biggest one, and the full modular subgroup, the full modular group, that's the smallest space. So for the spaces of modular forms, you have these inclusions here. Keep in mind that basically the space for the principal congruent subgroup is the largest one. We will need that in a second. Nice thing about these modular forms is that they have a Q expansion. So that goes as follows. Let n prime be the smallest positive integer that this matrix is contained in your subgroup. And then you can basically, it's periodic with basically n prime. So it must have a Fourier expansion basically in this parameter here. And then you can write it basically as this series in Q bar n prime. And that's very helpful for numerical evaluations. So now the main theme, basically what we will need when we calculate Feynman integrals, are iterated integrals. And in this particular case, iterated integrals of modular forms. So let now F1 up to Fn be modular forms for some concurrent subgroup gamma, and then define an iterated integral as we always define it, basically integrating up to the previous integration variable here, and iterate that n times if you have an iterated integral of depth n. Now, if you do that with rational functions, you know that an iterated integral of rational functions is not necessarily a rational function again. Usually you get logarithms and higher generalizations thereof. In the same way, an iterated integral over modular forms is in general not a modular form anymore. Same way as a logarithm is not a rational function. So now let's come basically to the real stuff. We look at elliptic Feynman integrals. Let's start basically with a case where I just have one kinematic variable. Here I drawn basically several Feynman integrals which are all elliptic and just depend on one kinematic variable, which is in this case minus p squared over m squared, where p squared is basically here's the external momenta, and all solid lines basically have a mass m. So basically what I will be saying applies to all of these Feynman integrals you see here. You can put all these Feynman integrals, the differential equation for them, into an epsilon form. You do that as follows. You first make a choice of two periods for your elliptic curve. Then you look for a fiber transformation, which will depend on the choice you made for the periods, because the periods enter explicitly in this transformation matrix U. And in addition, you perform a base transformation where you change from x, which was minus p squared over m squared, to the variable tau, which is more natural for mathematicians. So then you can transform basically your system of differential equations into an epsilon form. And let's look at a concrete example, namely the simplest one, the equal mass sunrise. Basically, you find your differential equation. You have three master integrals, one tadpole, two master integrals in the sunrise sector, and your differential equations then has this epsilon form, that the epsilon only appears as a prefactor, and here you just see modular forms. Now, these are not modular forms of the full modular group, but modular forms of gamma 1, 6. So one of these congruent subgroups I introduced before. So once you are basically in this form, basically, you figure out your boundary conditions, basically, and then you can solve systematically this differential equation. Oh, shit.
Is there a problem, Stefan?
Yes, my computer freezes. Can you still hear me?
Yeah, I can hear you, but the slide is the same as it was before.
Yeah, the screen is somehow frozen. I have a technical problem here.
I can also see you, and your image is moving, so maybe you can try to turn off the camera.
The problem is my mouse is not reacting.
Oh, I see. I see.
Can you give me 2 minutes? I shut down and reboot.
Okay. We wait. Stefan, I think we're back.
So
Hi,
I should,
Stefan.
yeah.
We
Sorry
can
for
see you and hear you now.
I do the screen sharing again.
Yes, that appears to work.
And now, okay.
Excellent.
We have been here, I think.
Yes.
Okay.
Maybe one more slide.
So, okay, now let's think about, let's go back to this slide. So I managed for a specific choice of periods to get a solution. So that's my solution, but somebody else might have made a different choice. So we now ask what happens if somebody else made a different choice for the periods. So, and we will be looking at a general modular transformation because they all generate the same lattice. So the first question is, which we have to address now, for a modular transformation, which is not in our subgroup, we have in general that f/k gamma is not a modular form of that specific subgroup anymore. The solution to that thing is whatever subgroup we have, by definition, it always contains a smaller subgroup, gamma of n, the principal subgroup of level n. And there we can show, since this is a normal subgroup, that this /k gamma operation transforms inside the space of modular form. So it might be a different modular form, that's okay. You just get something different, but you get, at least you get again a modular form. So that basically means question one, what happens under a transformation which don't belong to this subgroup you started with is solved by going to a smaller subgroup and basically this principal subgroup gamma of n, and then you stay inside this space. So that is basically the first question solved. The more complicated question is the second one. If you now look at iterated integrals of modular forms, we do a simple example, just look at an integral of depth 1 and see basically how a modular transformation acts here. Here I take the inverse transformations and this formula becomes a little bit nicer. And you see, I have here my original variables, then I do the transformed variables. I get basically f acted upon by the /k gamma inverse in this case. What I've written here in blue is everything fine because that's again a modular form. So that's what I would like to have. But in addition, you get here this automorphic factor. And only if I have modular weight 2, it's absent. Otherwise, it's there. So basically, you get to a bigger class of functions, including these automorphic factors. That's not nice. Because that's different the way it works for multiple polylogarithms. For instance, for multiple polylogarithms, you can think about these transformations here. And if you transform them, you always stay inside the class of multiple polylogarism. They might look different, but at least it's again a multiple polylogarism. And that's not what's happening with these iterated integrals of modular forms. So the solution to this problem is that you should not consider a base transformation, namely going from tau to tau prime, which basically is a coordinate on our base manifold. You should not consider this transformation alone, but always in combination with a fiber transformation. So you redefine your coordinates, and at the same time, you redefine your master integrals. Now, how does that work? For the equal mass sunrise, basically, we are interested in this modular transformation for a gamma from the full modular group. Then basically, okay, my tau transforms like that. So this is just what we would like to do. But in addition, we now basically also transform the master integrals according to this matrix. And you see basically the C and the D come from basically the transformation we are looking at. And basically the tau is our old coordinate. So it's a coordinate dependent transformation. And if we do that, basically, then one can work out and look at the differential equation for the transformed quantities. So we have the transformed master integrals, the transformed matrix A prime, and we can work out what A prime is. And it's basically very simple in this case. It's basically just the old modular forms acted upon by this /k gamma operator. And we've just seen basically if we're in the principal congruent subgroup gamma of 6, they are again all modular forms. So we see if we do the combination base transformation and fiber transformation, we stay inside the class of iterated integrals of modular forms. And that basically is what my colleague would have found. Basically, he would have said, I get as a solution iterated integrals of modular forms, namely those modular forms here in the variable tau primed. And so we say, see basically how basically modular invariance basically is realized in the systems of Feynman integrals. The fact that we need a fiber transformation is maybe not too surprising, because I didn't tell you how I defined my original master integrals of uniform weight. I basically divided the one with all propagators equal to 1 by 1 period. So here's the period enters. If my colleague would have done the same thing, he would have used his periods, namely psi1 primed. And this transformation here, this factor here, just adjusts for that. So this is not at all surprising. Now let's go to several kinematic variables. There, basically things necessarily are more complicated and more interesting. We have to talk a little bit about moduli spaces, in particular M1n, which would be the moduli space of an algebraic curve of genus 1 with n marked points. We can either view it as an algebraic curve of complex dimension 1 or as a real surface of real dimension 2. So that's also why the whole thing is equivalent to Riemann surfaces. What is interesting to us, basically, what are natural coordinates for these moduli spaces? So let's for a moment think about genus 0. So there we can use Möbius transformations, which are basically automorphisms of the Riemann sphere, to fix basically 3 points at prescribed values. And then only the other remaining points are free coordinates. So basically the natural coordinates for M0n are Z1 up to Zn minus 3 if you have n marked points. Genus 1, it's a little bit different. First of all, you only can fix 1 point at a prescribed value. So usually we can fix 1 point at 0, leaving us the remaining one free. But in addition, basically, we have one variable which describes the shape of the torus. Now, it can be a thick torus, a thin torus, or do not. So basically, we also have this variable tau. And that perfectly agrees with our previous case where we just have one kinematic variable, namely then basically M11, we have no set variables and just tau. And that's exactly what we did. We changed from the kinematic variable x to the variable tau. Now, if we have more variables, we have one tau and several sets. So we are interested basically in differential form, which only have simple poles. In the case of the multiple polylogarithms, these are just that. Obviously, you just have simple poles. And we have the iterated integrals of those. Now, the question is, what do we get on the moduli space M1n? And what it turns out that they come from the Kronecker function. So the Kronecker function, one defines first the first Jacobi zeta function, this definition, and then the Kronecker function is symmetric in Z and alpha, defined in this way. Then one expands the thing in alpha in one of the variables, and calls the coefficients, which are then functions of Z and tau, the coefficients of the Kronecker functions. And these will be the important ones. So just a few properties of those. They have only simple poles. They are not periodic. They are only quasi-periodic, meaning by a translation by tau, it's not the same function again, but you get additional terms according to that formula here. As well, basically, they are not modular, but just quasi-modular, meaning, again, modularity would just mean that you had in systems a term with j equals 0, but you get additional terms. So periodicity is a little bit spoiled, modularity is a little bit spoiled for these functions. So what you would like to integrate are now basically two types of differential one forms. As before, you can have modular forms. So fk is a modular form, and then you just put a d tau and 2 pi I to it. Then you get basically a one form. And that basically is all what we had in the case of one kinematic variable. But as soon as you have more mark points, you can get basically differential one forms coming from the Kronecker function, namely the following combinations. Basically, you have something which goes by d tau and something which goes by dz. And here, basically, I already gave the most general thing which we need to consider, where L of z is a linear function of basically my remaining z variables, and it might have a constant term. You can check that this combination is closed as it should be. So now the question is, how do modular transformations act on basically these differential one forms I just introduced before? And there's some small subtlety coming up. So you know, okay, tau transforms in this way. It's not too complicated that the z's transform in that way. If you just think about basically you mark one point and basically write it in the coordinates of one basis and then write it in the coordinates of the other basis, you find this formula. What you have to remember is that the constant terms here, basically here, these ones here, they also transform according more or less like the same formula here. And you can think about these constants basically as being mark points where you don't consider the dependence on. So basically you might think you actually have something in a higher dimensional space and you consider some coordinates fixed. If you change your basis, basically the value of this fixed coordinate transforms according to this formula here. So again, basically you only have quasi-modularity for these functions, and you are interested basically how do these lower terms drop out in your final result. Let's see how it works in a particular example. The simplest one with several variables could be the unequal mass sunrise. You have 7 master integrals, and you start with 3 kinematic variables, x1, x2, x3, which as a physicist, we would take those. Now, again, you can do the same thing. You can make a choice of periods. You can redefine your master integrals. You change your variables on the base manifold from x1, x2, x3 to natural coordinates on the moduli space M13. So you take tau, z1, and z2. And then once you work everything out, you get a nice differential equation with an epsilon factored out. The Cej are 7 by 7 matrices where just rational numbers appear as entries, and you get these differential forms, which are of the two type, either from modular forms or from the Kronecker functions, exactly the ones I showed you before. So that's
Stefan, you have about 5 minutes.
Perfectly fine. So
thanks.
This is basically what I get if I make a particular choice of periods. Now the same question, what happens if somebody else makes a different choice of periods? So basically he would then have transformed variables, tau prime, z1 prime, z2 prime, and also these constants transform. So if my constants would be 1, they wouldn't be 1 anymore afterwards. So we do exactly the same way a thing as before. We say, okay, we need also a fiber transformation. In that case, basically, the fiber transformation is 7 by 7 matrix. It's actually not too complicated and basically given here. So you see, it depends again on the modular transformation you're considering, on the variables, and also on the dimensional regularization parameter. And doing so, you can show basically that you stay inside the same functions you started with. Iterated integrals of modular forms and of the things which come from the Kronecker function. Now, 3 comments. Why do we bother at all about how that behaves for modular transformations? The reason is we evaluate these iterated integrals by their Q expansions. These Q expansions converge if Q absolute value is smaller than 1. If we know how basically we perform modular transformation, we can always map tau to the fundamental domain, and then my Q basically the absolute value is smaller than this number here, which is a very small number, and we get a very fast converging series. So this is of practical importance because in the end, if we want to do phenomenology, we would like to get a number, and that's a fast way to get a number. One word about uniqueness of master integrals of uniform weight. It's clear if I have a set of master integrals of uniform weight and I do basically a transformation which has just constants in it and is invertible, then again I have another basis of master integrals of uniform weight. And you would say, yeah, this is trivial, and I agree with that. But what we have seen now, we can actually do a transformation which depends on the variables on my base manifold, which basically is really x dependent, and transform one basis which is of uniform weight into another basis of uniform weight. And the two transformations I showed you for the equal mass sunrise and the unequal mass sunrise, they are exactly of that type. So meaning maybe we shouldn't use the word canonical in this context. Last comment, basically, we expect that the choice of the periods does not matter. Can put it a little bit stronger, saying that we expect that whatever choice of periods we choose, we end up in the same class of functions. And that, if you assume that, will put some constraints on the matrix of your differential equation. As an example, just think about one master integral depending on two variables with a differential equation like that. Then basically if A is of that form, basically whatever choice you make for your periods, basically you will stay inside the class of functions of basically modular forms and these Kronecker functions. However, if you think basically maybe my matrix A looks like that, you will not stay inside this class. It's not modular. If you do a transformation, you will get iterated integrals which contain in addition these automorphic factors. So you see basically you get additional constraints here. And that might be helpful for bootstrapping basically what this matrix A could be. And it's on top of the constraint you always have that this matrix needs to be integrable. Both of them here are. And that basically brings me basically to the conclusions. So the main motivation of this talk was to see basically to study how things change basically if I change my periods of the elliptic curve. Reason for doing so is basically first of all for numerics. It's a good thing that I can always transform Q that it's a really small number. We've seen basically that we have basically x-dependent fiber transformations which transform integrals of uniform weight into integrals of uniform weight. And we've seen that modularity puts constraints on the matrix A. What we've also seen, and this is a little bit a minus now, that we see that we basically, if we just work with iterated integrals of the type we've been discussing, modular forms and Kronecker things, then we cannot write a black box numerical evaluation algorithms like we have for multiple polylogarithms, which just evaluates basically a linear combination of these iterated integrals for us for all possible values of the variables. Why? If we do a modular transformation, basically we leave basically this class of functions. We only get inside this class of function again if in addition we change the definition of the master integrals. But for a black box algorithm, you don't want to specify the information on the master integrals. You just, I mean, if you use GNAC for multiple polylogs, for some Feynman integral, you say you have a long list of polylogs, please evaluate them at this point. You don't say they come from this master integral and you can transform the whole system of the master integrals. So that's basically, keep in mind that. With that, I thank you for your attention. And yeah, I'm looking forward to questions.
Thank you very much, Stefan, for this nice and pedagogical talk. And I see that we already have some questions, and I think that Oliver was first by a nanosecond or so over Simon. So Oliver, you go first.
Yeah, thanks a lot, Stefan, for the great talk. I'm wondering how much information about the modular transforms you discussed are encoded in the gamma twiddles, in these Brown-Levin style elliptic polylogs that appeared in both the string theory literature and in QFT? Suppose I'm sitting on all modular transformations of the gamma twiddles. How far would I get in reproducing the results of your talk?
Very far. So the gamma twiddles, basically I discussed here these differential one forms. So just think for the simplicities that L of z is simply z, one z. And so this is basically an integral in dz, and that is basically something in d tau.
Okay.
So this is a differential one form which lives on this moduli space. Now you can decide basically how to integrate basically your differential equation, where you put your boundary condition and in which way you move to the point you are interested in.
Okay.
So my preferred way would be to integrate in tau, because I think this is the simplest one. But other people might prefer to integrate in z. If you do that, say you choose a point where z takes a specific value, where you know the boundary value, and simply integrates the differential equation in z, this is perfectly legible, perfectly okay. And in that case, you get exactly this gamma twiddle things. So the gamma twiddle things is nothing else than integrating these differential one forms in Z. And all the results apply.
And is there a place in the literature you would recommend or a technique to compute the modular S transformation of specific gamma twiddles?
Oh, now, as I said, basically, it's very simple. In order to figure out basically this transformation matrices for Feynman integrals, it's rather simple. I mean, it's a rather simple matrix because it has mostly ones on the diagonal, and this one basically you can figure out very easily. Once you have that one, all the other ones follow more or less rather simple. But you will need the information on the Feynman integrals they come from. Now, what you want is basically you just want to discard the information on Feynman integrals and just look at linear combination of gamma twiddles. So I'm missing the information what the fiber is.
Okay.
I would not know basically, probably there's a way to figure that out, but let's say if you keep the information from which family of Feynman integrals it comes from, it will be much simpler.
Okay.
I think we have to move on to Simon because the time is running.
Sure. Thanks a lot.
Okay, I have a quick question there. Well, thanks a lot for the talk. I missed the first half, so maybe you answer it. My question is about this this modular transformation. So SL2Z can be represented like the modular group can be represented as 2 by 2 integer matrices, right?
Yes.
Is there a way to understand this matrix U in terms of representation of SL2Z? Like, I would have expected naively that there should be a way to find a basis where one of the subblock is just a standard SL2Z matrix. Does that make sense, or is there an obstruction to that?
Would not know the answer immediately. The simplest, well, so you're asking about the matrix which transforms the Feynman integrals,
Yes.
if they can be decomposed into representations of SL2Z.
Yeah.
I cannot answer this question out of the pocket. What I would do basically takes the simplest example here. This F0 is -1. You have this matrix here. See how far you get, basically. And
yes.
So I would have to sit down and do the calculations, basically. Never thought about that question.
Okay, thanks.
So now, Niels.
Hi, Stefan. Thanks for your talk. I have a question about these groups, these modular groups, gamma of n, gamma 1 of n, gamma naught of n, that appear. So in the sunrise case, I think the relevant group is gamma 1 of 6, if I remember correctly. And I was wondering if there is some expectation how general congruent subgroups can be that arise in the Feynman integral context. So other groups that you may have encountered, or maybe just what is the expectation of physicists? How general does it get within the class of congruent subgroups?
Okay, I can give some comments on that. So if I have a particular nice representation of my periods, I end up in gamma 1, 6. Gamma 1, 6 has 4 cusps, namely at 0, 1/2, 1/3, and infinity. And my original differential equation has 4 singular points where x equals basically 0, -1, -9, and infinity. And these singular points of the differential equation are all different, are mapped to different cups of the congruent subgroup. So I would say you would always need a congruent subgroup which has as many cusps as you have singular points in your differential equation. Now, if you do a modular transformation, you end up basically in a smaller subgroup, meaning the space of modular forms is bigger. So basically I can make maybe not an optimal choice of periods where I would recognize basically all my modular forms of being of gamma 112, which basically is a smaller group. That's still okay, the result is still correct, but then basically some of the cusps basically correspond to the same singular point of my differential equation. So that is basically the best information I can give you basically on this question.
Well, the time is very tight, but David raised his hands some time ago. So David, I hope you can be brief.
Yeah, in the examples that you've shown, the tau parameterizers, the momentum dependence and the extra variables will be mass ratios. Have you actually considered situations in which there is more than one external momentum?
We are working on that. There should be no principle. Well, let's put it like that. We have one situation which we study carefully. It's more complicated because this is a situation which then depends not on one elliptic curve, but on 2 elliptic curves. And that's the reason why we're interested in. I would not know about an example. Maybe I would have to scan through the literature. Probably there are, where you just have one elliptic curve. Oh yeah, this box graph basically with 10 external legs. So I think there should be only one elliptic curve in that one, but I'm not the expert on that. And you have a bunch of, you just have external kinematics there.
That's the only example I know, the 10-point function.
So Stan, if you have a really quick question, you can squeeze it in. Apologies.
Yeah, it's a brief question. It's about slide 24. Can you say briefly how you got those specific functions of 0 to 4, and what kind of function class you expect in general for this epsilon form?
So how did we do that? Basically, we first assumed that we should change the variable from x to tau. Okay, let's put it now. We do it in 2 stages. The first stay with x and just write basically find Fourier transformation in x, the periods and the derivatives of the periods, which just bring out the epsilon in front. So that you can do. You have to calculate with complete elliptic integrals, but it looks a little bit messy. You can do that. So then you just have the epsilon out. And here you have basically horrible functions depending on x, the periods, and derivatives of the periods. Then you say, that's of course the insight, you say, well, maybe let's change from x to tau. You basically substitute for x tau and write down the Q expansion to very high order, 100, 1000. And then you simply check, basically, does it fit any known modular forms? Basically, it does for as many terms as you want. So it's not a strict proof that it's actually like that, but basically, if you can do it for the Q expansion up to order 1000, as a physicist, I would say, yeah, that's more than what I want.
Okay, I think we need to stop now. And